Hi everyone, I'm Ali and I'm going to be talking about some theory work I did with Michael Dennis and Stuart Russell at Berkeley, understanding intrinsic motivation and exploration. So, reinforcement learning addresses the challenge of maximizing rewards while learning in an uncertain environment. This is difficult in environments with sparse rewards, and a common solution is to add intrinsic rewards to guide the agent's exploration, which we call intrinsic motivation. There has been a proliferation of different forms of intrinsic motivation, many inspired by psychology and cognitive science, actually, and some even seemingly at odds with each other. And there are countless edge cases where they cause bad behavior unexpectedly. For instance, if we use positive surprise, which rewards the agent, can you hear that better? Sorry. By how poorly it predicts the next observation from its previous experiences, if its environment contained a noisy TV screen that randomly flips channels on the right, even an optimal agent would be glued to the TV because that always yields more rewards than exploring the more predictable maze. We can understand how to avoid these sorts of problems by analyzing and designing intrinsic motivation within a theoretical framework for how an optimal agent should explore. Such a framework already exists, the Bayes Adaptive MDP, or BAMDP. So, BAMDPs formulate the RL process as starting with a prior over the uncertain world, modeled as a Markov decision process M, and learning more about it through experience. For clarity, we assume only the reward function R and state transition dynamics T are uncertain, while the state and action spaces S and A and the discount factor gamma are known. The BAMDP state augments the underlying MDP state S with the history H of states visited, actions taken, and rewards collected so far. The RL agent, which decides how to act based on what it has experienced, is thus a policy mapping BAMDP states to actions. The reward function takes the expectation of the underlying MDP's reward function over the posterior P of M given HT. The transition function is analogous. So the optimal policy for a BAMDP is the RL agent that explores optimally for that setting. And unfortunately, this is intractable in general because it requires planning through future beliefs. So RL algorithms typically act implicitly or explicitly to maximize a value prediction estimated from experience. How well they perform reflects how accurate their prediction is, and we can understand intrinsic motivation as compensating for RL agents' misestimation of this value in the BAMDP. For further insight, we decompose the BAMDP state value into value of information plus value of opportunity. Value of information is how much more value an optimal agent would get from its current state than if it only had its prior knowledge, H0. And value of opportunity is just the value of the current MDP state under the prior H0. These components give us a new typology for the different forms of intrinsic motivation based on which type of value they signal. Widely used RL algorithms tend to underestimate VI. Thus, intrinsic motivation commonly adds it back with positive rewards where it is expected that the value of information is increased. For instance, surprise signals that the more unpredictable an observation is, the more valuable information will be obtained from it. Meanwhile, it can be difficult to initialize RL algorithms with all the prior domain knowledge, so VO is an easier way to specify that we know a priori that certain states are more or less valuable than others. For instance, negative surprise, intrinsic rewards, signals the knowledge that this environment has danger in its more unpredictable areas. Failures of intrinsic motivation can be understood as the intrinsic rewards not aligning sufficiently with the true value. For instance, in the noisy TV problem, watching TV has the highest surprise but the lowest value of information. In addition, we show that only intrinsic motivation in this form, which we call BAMDP potential-based shaping functions, or BAMPs, always preserves optimality and approximate optimality of RL algorithms. The potential function phi typically signals the desirability of a BAMDP state, encouraging RL algorithms that increase their potential from the current state, SH, to the next, S prime, H prime. So here we visualize, over 3 snapshots in time, an example of a BAMP with the potential set to the number of unique MDP states visited, signaling the value of information of having explored a wider range of states. In this MDP, the agent starts at the white grid cell and is reset back to that position every 50 time steps. The only reward is at the goal cell marked in green. Over time, as the agent reaches more unique states, it must travel further from its initial state to get rewarded. Thus, if we use BAMF intrinsic motivation, as we generate increasingly optimal RL algorithms, which could be with meta-learning, lifelong learning, or manually as a field, we guarantee they will also be increasingly optimal for the underlying problem. And we can convert intrinsic motivation terms to BAMFs by taking the component of BAMDP value they signal and setting that as the potential function. Please stop by my poster session tomorrow to learn more. Thank you.